So Rebecca went on a bike ride. This graph shows Rebecca's distance from home on her bike. Notice distance from home because we talked about this or mentioned this distance from home. Okay, so hopefully it's a really good idea when you've got a question just to check that you understand the question, the information given before you go bother with the questions. So distance from home in kilometers, okay, time in minutes. Okay, so here hopefully we know what can we say about this bit. She's traveling at a constant speed because that line is straight. It is a constant speed, and this is easier now. We can see if you look, so this is 30 minutes split into 3, so each one of these is 10 minutes. In 10 minutes she goes 2 kilometers. In another 10 minutes another 2, another 2, another 2, another 2, so it's constant speed. Here she stops, here she returns home, but quicker. She's going faster. She is going faster than she is here, but it is still a constant speed. So, question: how far had Rebecca travelled after 30 minutes? So after 30 minutes means that we're starting at 0 and it's after 30 minutes. So what we can do is we can read up, find out where the graph is, and then read across. That's 6 kilometers. So she's travelled 6 kilometers after 30 minutes. After 60 minutes, Rebecca stopped for a rest. How many minutes did she rest for? Okay, so we saw this bit stationary because time is still continuing, but distance is not changing. And she's gone from 60 to, and when I said about these are each 10 minutes, it's a good idea to do that to get to grips with the scale. 3 squares is 30 minutes, so each square, just do 30 divided by 3 is 10. So each square is 10 minutes. This is 2 squares, so 20 minutes. How far did Rebecca travel in total? Okay, careful here. She travelled 12 kilometers to begin with, and then she travelled 12 kilometers back. Okay, so in total it's 24 kilometers. Yeah. Now, this is what I wanted to show you before, but I just want to get on to practice. So these are all different graphs, and it's really useful to start just being able to glance at a graph and explain what's happening. So I'll just read this bit and then I'll give you the opportunity. Jess drove from Leeds to Liverpool. She stopped at a service station. Sorry, she drove from one place to another, Leeds to Liverpool. She stopped at a service station for 30 minutes on the way. Which of these distant graphs could represent? Oh, okay, so what I'd rather you do is just think about what each of these is showing. So here, look, she's got a constant speed. She's stopped. Oh, look, it's distance from somewhere rather than just distance. So she's travelling away from Leeds, she's stopped, and then she returns, but she's going slower. Gradient is less. On B, she's going at a constant speed, but she's always moving away from Leeds, and she never stops. Her distance is always increasing. C, she travels away from Leeds at a constant speed, and then she returns. She does not stop there. There is no stationary part. She just drives there and then drives back. Slightly slower on the way back, the gradient slightly less. Here, she drives away from Leeds at a constant speed. She stops, and then she's still travelling away from Leeds at a slower speed, but she's still travelling away. Her distance from Leeds is still increasing. E, she starts away from Leeds. We don't know where. Let's not assume Liverpool, could be wherever. She is moving towards home at a constant speed. Hate that. I haven't told you never ever have vertical, so we could presumably zoom in and find that that is not quite vertical, but she's got a staggering speed to make it look even like it's vertical. So look, her distance, say her distance here from Leeds is 80 kilometers, and then her distance here is 60 kilometers. She's done those 20 kilometers in almost no time. So I'm baffled by that, but that's not what it's testing. It's not saying these graphs are all correct. It's asking you which one is the graph correct for her journey. So even if it is vertical, they're not suggesting that that graph is correct. And then F, she moves away from Leeds at a constant speed. Then she sort of accelerates, but in one step. She changes from maybe 40 miles an hour to 60 miles an hour. There's no sort of acceleration as such. She just changes speed because the lines are both straight. So, oh, I thought she returned. She drove from Leeds to Liverpool. Oh no, no mention of returning. She stopped at a service area 30 minutes. Which of these? So she's driving away, she stops, she's driving away. So it's got to be D. On A, C, and E, she returns home. It's only B, D, and F that she's continually moving away from Leeds, but she doesn't stop in F or B. Right, Bill is a taxi driver. You can use this graph to find the cost of a taxi for different distances. Okay, so we can apply what we use for distance time graphs to all graphs. There's differences, but there's similarities. So have a look at this graph. Now this is a funny one. As you can imagine, in a taxi, the further you go, so it's not time down here, now it's distance. The further you go, the more the journey costs. Okay, so you can still kind of imagine moving up, right? Distance increasing, and the cost is also increasing. Okay, as you go up in distance, you go up the y-axis, so the distance increases. But look at this, at 0 miles there is already a cost, and it always asks this. Oh, how much is the fixed charge? Okay, £5. Often it'll say, why does the graph not start at 0, or why does it start at 4, or something like that. And that's because in a taxi you have a fixed charge. You may have one, another example they use is if you're hiring something. Okay, because what you don't want for a taxi or for a hire, if you're hiring a drill, because you want to do some drilling, what about if the shop that I'm borrowing the drill from is just there? I can go over, borrow a drill for like 4 minutes, drill a couple of holes and then return it. And if there's no fixed charge, then say it's, even if it's £100 an hour, let's make it £60 because there's 60 minutes. For 4 minutes, I would only pay £4. And that is not a business model that's going to make any success. Likewise, if a taxi didn't have a standing charge, then I could just nip round the corner. Can I get a taxi from here to my bedroom, please? And they would make next to no money. So that's why I have a standing charge. Bill makes 2 journeys. Cool, Bill. The distance of one journey is 10 miles further than the other journey. Work out the difference between the 2 journey costs. Okay, so because this is a straight line, you might be thinking, well, you don't know how far, it's 10 miles further, but we don't know how far it is. Well, because it's a straight line, it doesn't matter. If we go from 5 miles here to 15 miles here, and we work out the difference in distance, it'll be the same if we went from 10 to 20 or 15 to 25, okay? But I'll just try and scribble this on here. So from 5, if we go up from 5, it's going to look a bit awful because it's not with a ruler. What you do is you draw a line up to the graph. I think that's halfway up that square, so I think it's just halfway. So it's halfway between here and here. So this is 10. Each one of these is therefore 1. So this is 12.5. So it starts at 12.5, which is pounds. So remember that 0, £12.50. And then 10 miles later, I reckon this is half as well. So it's there. Sorry, halfway between these 2 squares. So that is going to be 27.5, aka £27.50. So then you just work out the difference, and it's £15. So the answer is £15. Okay, there you go. 2 marks, so you need to include your workings. So what I would do here is say, yeah, 5 miles costs £12.50, 15 miles costs £27.50. Therefore, the cost of 10 miles is £15. I'll kind of keep going through here until we've done 15 minutes, because in fact I might skip. How many questions are there? Oh, there aren't that many. Just to go to the hardest questions. Is that where we were? No. Right. John draws a graph to show the amount of petrol his car used on a 250-mile journey. So before you get to the questions, let's understand that graph, because first of all, it's going down. It's a negative gradient. Like, ooh, okay, that's different. So petrol, so it's the amount he used. So as distance increases, the petrol, oh, okay, look. I'm sorry, but that's just wrong. This is not the amount of petrol he's used. This is the amount of petrol he has left in his tank. The amount of petrol you use isn't going to decrease, is it? The further you go. So the distance is increasing here, and hopefully you're getting a grasp for, once you understand the graph, you can sort of start to see it a bit better. The distance is increasing and the petrol is decreasing. So they're obviously talking about the petrol in the tank. There's no other petrol that, as I drive to Sheffield for 3 hours, there's no petrol decreasing apart from in my tank. So that's what we mean. So it kind of shows how much he used, but I think it's a bit misleading. How much petrol was in John's car? Oh, well, now it refers to it. Was in John's car at the start of the journey? Well, it's right up here. It's 45. Good. 45 litres. Whenever there's units, if it's given, fine, but check. Otherwise, you should be in the habit of always writing litres or the units. It's a waste of a mark. How many more miles can John's car travel before it runs out of petrol? Ooh, okay. So, first of all, we want to work out how much petrol has he got left. Okay, he's got 10 litres left. 10 litres left. And then, of course, we want to know, well, how far does he go in 10 litres? Okay, so what I might go do back here, they've used this triangle, but I'll show you so that we've got a new example. Because, can I scroll up? Because it's a straight line, again, we can use any part of the graph. Because he used in 10 litres, the beginning of the journey, the amount of mileage he got in 10 litres was the same in the middle of the journey, was the same at the end of the journey, because it's straight. The number of litres of petrol he has left falls constantly as the distance increases. So 10 litres, I mean, we've got 45 here, so why not go to 35 here? So we know here there was 0 distance, and if we can work out, notice, by the way, before I draw my line, I am going down, I'm going to establish exactly where I think that is. And I've sort of drawn over the point, so that's annoying. So look, I think this, if I go along here, because this is on a nice line, I reckon it's slightly into this square, but because I'm just looking at this bit there, I think we'll call it on the line. You'll see that we always allow maybe half a square. There's always room for error because you're reading off a graph. So I only go down here, and so I've already determined where it's going to be down here. So it saves me going stray. In fact, what I can do is I can mark that down here and then go down to it. Blah, 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 blah. So that distance, if this is 50 and there are 10 squares, then 50 divided by 10 is 5. So each square is 5 miles. So he's gone 50 plus 5, 10, 15, 20. So he's gone 70 miles. And look, I think we're right in the middle of their range, maybe. I like to be spot on. 70 to 2, okay, but they've said the range is 70 to 2, so 71 is what we wanted. Oh yeah, and of course if we'd have been as accurate as we could possibly be, I think it was slightly over the line. But anyway, as long as you're reading properly, you're going along this line and then down, you are going to get the mark. What assumption have you made? Have you made to calculate your answer to be? Okay, so. I don't much like that question either, because I'm not sure that we've assumed that the use of petrol is constant. It's shown on the graph, but there you go. Yeah, I mean, of course we're assuming. I'm assuming that no, better answer would be that the last part of his journey would use the same amount of fuel. You can imagine, for example, and sometimes it is tricky to think of these examples, the lighter a car, the less fuel it uses. In Formula 1, they don't want a full tank unless they have to. So it's a big decision, isn't it, whether they pit 2 or 3 times, because the less fuel they have, the faster they go. But of course, then they have to stop for fuel more often. So you would actually expect the number of litres, the gradient to decelerate. So it would start using slightly less fuel. So it sort of go, if you can see my mouse, a bit like that. I mean, I've exaggerated the curve there, but yeah, we're going to assume, I think what they mean is the same rate for the last 10 litres. We've taken a pattern, which is all the way from a tank of 45 litres to a tank of 10 litres, and we are extending that pattern. So we don't know that that's the case. We don't know that we can do that, but we've got no other information, so that's what we're doing.